Welcome back. In this portion of the lesson, we're going to look at a couple piecewise functions. All right, so here we have the limit of x plus 4 if x is less than or equal to 3, x squared minus 2 if x is greater than 3 as x approaches 3. And so we're going to do a table here of values so we can look at what happens on the left and right hand sides. Right? So when you have a piecewise function, you have to make sure you plug into the right part. Right? So if my values are less than 3 or equal to 3, I'm going to plug into x plus 4. If my values of x are greater than 3, I'm going to plug into x squared minus 2. Right? So for 3, right, f of 3, that would be 3 plus 4 or 7, right? Because I have to plug into the top function for all the values of x that are less than or equal to 3. Right? So this one's going to be 7. Right? And if I have 2.9, right? So f of value of the function for 2.9, I'd still plug in to the first part of the function. Right? So that would be 2.9 plus 4, 6.9, right? And so on for all these values that are less than or equal to 3. Right? So 2.8, I'd have 6.8. And then 2.7, we would have 6.7. Right? So now, how about for values that are greater than 3? Right? So now we're going to use the other function. So for 3.1, for instance, f of 3.1, now we would have 3.1 squared minus 2. And now I'm going to be really liking a calculator. So I don't have to square necessarily 3.1 in my head. Right? Right, so if we take 3.1 and square it, right, and then subtract 2, right, so we have 7.61. Right, and same thing if we have 3.2, you have to remember not to write on the board or the calculator goes away. I'll have to write on the board, not the smart board. All right, so 3.2 squared is going to be 10.24. If we subtract 2, that would be 8.24. All right, so I'll just remember that's 8.24. Right, and then if we plug in 3.3, and then subtract 2, we'd have 8.89. All right, so let's put those values on the table. So 8.24, and that was 8.89. Well, they're kind of close to one another, the 3 and the 3.1. Right, and the 2.9. You know, it looks like maybe they're going towards 7, but it's kind of hard to tell. Right? Maybe if we chose values that were even closer, it would be easier to tell. Maybe we should graph this and see what it looks like on the graph. And maybe that will help us see what the limit of our function is. Right? So let's take a look at the next page where I have a graph. Okay, and so we're going to find the limit, and it was x plus 4, and that was if x was less than or equal to 3, and x squared minus 2 if x is greater than 3. Right? So right at 3 here, I'm just going to put this is not a vertical asymptote. This is just sort of like an imaginary wall, and we switch functions here. Or we switch parts of our function. the breaking point. It's where we go from one part of the function to the other. Right? Right, so at 3, right, if I plugged in 3, right, we'd have 7. We saw that. Right, so we have that point there. Now let's think about the rest of this, right? So our graph here, well, that's just a line, right? X plus 4, right? So that's a line with a slope of 1, right? So my next value is going to be 4, right? And then, excuse me, my next value would be 8, right? So oops, I'm sorry, I'm on the wrong side. Wrong side. Less than. Got to pay attention which side's where. Sorry, so our next value would be f of 2, right? And then f of 1, f of 0, right? So on the left-hand side, well, it went downhill. On the graphing, right after 0, that's not very line-like. I should use a line tool. Right, so our graph looks like that on the left-hand side. How about the right-hand side? On the right-hand side, we have a parabola, right? And so when x is 3, right, 3 squared minus 2, it's going to be 9 minus 2, or 7. Right, as well. The next value is going to be impossible to graph, right, because that would be 14. But you have the idea that it would be a parabola that's going to go right off my graph like that. Well, if I look from the left-hand side and I look from the right-hand side, there's no breaks in my graph, right? I've got a line and a parabola. They're continuous. They just switch which function I use. It switches at 3. So notice that the limit as x, the limit of our function x plus 4, I have to write the whole thing. If x is less than 3, x squared minus 2, if x is greater than 3, as x approaches 3 from the left, equals 3. I should put parentheses around this whole thing. And the limit, and again, x plus 4 if x is less than or equal to 3, and x squared minus 2 if x is greater than 3. As x approaches 3 from the right-hand side is also 3. Therefore, our limit as x approaches 3, I don't know how that got left off, the limit of x plus 4, the whole thing there, as x approaches 3, is going to be equal to 3. That's supposed to be an equal sign. That's not a funky new symbol. Just going to drag it up. Right, and it equals 3 because the limit as x approaches 3 from the left equals the limit as x approaches 3 from the right. So one kind of problem with when we're finding our limits numerically is if I'm not close enough to 3, sometimes it's hard to tell. So it's kind of hard to tell. Is it going to go to 7 on both sides? And when we're at 3.1, we're at 7.61. So numerically, you should probably choose values that are even closer to 3, right, to make sure. With our graph here, because we know how to graph this function, right, we can see that it's approaching the same value. Did I put equals 3? I'm sorry. It's x that's approaching 3. Our limit's approaching 7. Our limit is 7, not approaching. Limit is 7. As x approaches 3, the limit is 7, not 3. Right? So back here, I wrote 3 too many times. The limit as x approaches 3, we can tell from our graph now, is 7. All right? Oh, and I never bothered to write anything. Well, I'll write this one down since I did. 7.61. There you go. Right? So with a piecewise function, you just plug into whichever portion is indicated by the value of x. Right? And if you can't tell when you find your values, maybe you need values that are a little bit closer, right, to the value that x is approaching. Right? But in this case, the graph helped us out, and we can see that our limit is indeed 7. Right? One more example. We want to find the limit of the following using a table of values. Right? So this one I'm not going to graph, well, because I would need a very big graph. If you look at the functions there, they get kind of large. But I do have two tables. Right? Let's look at the first table. So here, we're looking at what happens as x approaches 5. So I chose values that were 0.5 away from 5, coming from the left and from the right. Right? So 2.5. So our function, I should read our function. Our function, we're finding the limit of x squared minus 2 if x is less than 5, 7x minus 2 if x is greater than or equal to 5. Right? So for values on the left-hand side, we're plugging into x squared minus 2. For values on the right-hand side, we're plugging into 7x minus 2. So as we're coming from the left-hand side, the numbers are getting larger, right? 4.25, then 7, then 10.25, then 14, then 18.25. Once we get to 5, we plug into 7x minus 2, and that gives us 33, 36.5, and 40, and 43.5. So is the limit equal to some value? Right? What's the left-hand limit? What's the right-hand limit? It's hard to tell because we're not very close to 5. So let's get closer to 5 and see if we can tell. So now I plugged in values that were much, much closer to 5. 4.9, 4.99, 4.999, right? So we're very close to 5. Right? So now let's look at our left-hand limit. Right? So 22.01, 22.9001, 22.999, 22.9990001. Right? I think that was supposed to be 22.99 and 0001. I think I ran out of space and left off some of the zeros and decided just to use that much of the number. But as we look, it looks like on the left-hand side that the limit as x approaches 5 is equal to 23. Right? So as we're coming, what happened to my 2? I said 23. All right, so as we're coming from the left-hand side, it appears that our function is approaching 23 as we get closer and closer. As we're coming from the right-hand side, however, right, notice our values are getting, if we look from the right, they're getting closer and closer to 33. Right, so the limit of f of x as x approaches 5. Does that exist? It does not exist. And the reason this limit does not exist, I don't know why I did that. I'm going to say f of x. I'm smart this time. I did not feel like writing that in. So f of x equals this. If you ever switch and write f of x instead of a function and it's not labeled f of x, make sure you label that function f of x on an AP exam so that's clear to the grader. But I'm not going to write that anymore. So the limit of f of x as x approaches 5 does not exist because the limit, we'll put a because in here, the limit of f of x as x approaches 5 from the left does not equal the limit of f of x as x approaches 5 from the right. right? So because our one-sided limits, although they exist, right, because they're not the same, the two-sided limit does not exist. All right, so now you've actually learned one of the ways that a limit might not exist. It's not going to exist if the left-hand limit doesn't equal the right-hand limit. It's not going to exist if we don't approach a finite number. But there are other ways that a limit might not exist, right? And there's at least one more. And we'll learn about that in a future lesson. Maybe the next lesson. Right? So that's the end of numerical limits. Thanks for watching. Bye for now.